I don't know if I have it on me physically, easy to find. It's negative. Yep. Yeah. All right, guys. So, so we're going to take a little bit more formal of a look at what we were doing yesterday with breaking up that area under the curve into rectangles. So our first example, the graph of g of x is shown to the right, and we want to approximate that area under the curve on the interval from x equals 2 to 6 with n subintervals by using a left rectangular approximation method. So when we draw these rectangles in, and we saw this because we did each problem twice, we got an overestimate and we got an underestimate. It depends on which side of the rectangle you want to go up to the curve with. So this says to use a left method. So I'm going to draw each of my rectangles from 2 through 6 in by going up to the curve on the left and then coming over to the right. Now, when I did this, we can do this. You'll notice they actually didn't give us a number of subintervals here. I started drawing them in before I really read that and remembered what it was asking to do here. But we could do that with any number of subintervals. The thing that I think makes the most sense, especially like day 2 of doing this, we're going from 2 through 6, so follow the grid lines and make 4 rectangles. So if I use 4, I get 4 rectangles with width of 1, which is nice. When I go to do length times width, whatever my length is, which is the height of the rectangle, that's just the value of my area because I need to multiply it by 1. So when n equals 4, I would end up with my first rectangle having an area of 2 times 1. We've got to estimate here a little bit. The height of this, I'd say about 2.3. So we'll say plus 2.3 times 1. If they'd given us the function, we could have actually plugged these values in. 4 looks just a hair lower than, above that line. So I'm going to say 3.2. And then finally, for our fourth rectangle, that has a height of 4.6. Yeah, that's what I would say. So adding those up quickly, it looks like we have 5.5, 7.5, and then 11. No, sorry. Wait, what did I say? 7.5, and then 11.5, 12.1. There we go. Is the real area under the curve bigger or smaller than that? Bigger, yeah, absolutely. We made an underestimate there. And we'll talk about that. Probably not. We'll see how far we end up today. Now, if I had done that with n equals 8, what would change in my sum there? What are some of the changes that would happen here? Right. So all of our widths would be a half. And we'd have a lot more numbers, right? We'd actually have 8 numbers instead of 8. I guess I should say 8 areas instead of 4. Widths would be a half. And I think I heard it. What did you say? Yeah, it'd be more accurate. Yeah, closer approximation. We're going to do a bunch of these today, so No sense in doing all that math. We'll have a little bit better. We'll actually have the function we do it better. So this approximation method that we're doing is called a Riemann sum. So it's R-I-E, spelled right below too. R-I-E-M-A-N-N sum. Comes from a guy who made it up, Bernard Riemann. And we have the thing that we're doing, which is the integral, which you guys took the note on the card this morning. The mathematical symbols we use to represent the area under the curve is the integral. And the way that we show that is we use this symbol, which is an integral. We put our interval from low to high on the top and the bottom of that integral. And we say which function we're measuring the area under the curve with, and that's going to be f of x. We have one more piece to this. We'll talk a little bit more about this in the next lesson, about where it comes from. But in the end, it's really similar to our dy dx notation. When we take our derivative, we have to take our derivative with respect to a variable. When we integrate, we have to integrate with respect to a variable. We have to know where we're drawing these rectangles from. You could, and later on in later chapters, we might integrate with respect to y. In that case, we would be thinking about drawing rectangles off of the y-axis instead of the x-axis. So this piece doesn't actually, it's nothing we have to do anything with. It's just telling us what we're integrating with respect to, where we're finding the area across from, and that's sort of what's going on there. This is our integral. This means the area under the curve from A to B. Okay, we're going to learn how to solve these. We're going to learn what to do with them. But for right now, this thing is our area. Sort of just like, f prime was the slope of the tangent line. We learned how to solve it. But in the end, if I have f prime, I have the slope of the tangent line. If I have this integral, if I knew what this was equal to, I would know this area. Okay? Alrighty. Okay, so what we're going to do is we're going to practice the 4 types of sums. So there are 4 different ways to do these sums. We're going to practice the 4 of them. There's a left sum and a right sum. And then on the next page, we're going to do a midpoint sum. And the very last one that we'll do, which is actually kind of the best of the group, doesn't use rectangles. So we'll talk about all those. I don't know where it is off the top of my head. And if we had more time, so I think we'll just do it second period. Yeah. So I thought I had kind of mumbled that to you earlier. Okay. All right, so left Riemann sum. This is the same thing we were doing up top. They want us to go from 2 to 8, and we're going to use 3 subintervals. If we need, I don't want to say an approximation, if we need a value that we can't just read off the graph, we'll use this function, 4x minus 1/2 x squared. So we're going from 2 to 8. We're using 3 subintervals. So that means how wide are our blocks going to be, or how wide are our rectangles going to be? 2. Yep, we're going from 2 to 8. Each rectangle is going to be 2 high. Or 2 wide, I should say. So we're doing a left sum. So my rectangle goes up to the curve on the left. That's easy to measure. Goes up to the curve on the left. And goes up to the curve on the left. Notice in this situation, some of our rectangles underestimate and other ones overestimate. Just visually, what would you say we're going to get here? Are we going to get an overall an underestimate or overall an overestimate? Yeah, definitely an overestimate. There's a big chunk of rectangle that we're measuring here that is not under the curve. And it's, I think, bigger than this piece here, not to mention that one. So again, we're just finding areas of rectangles. Finding the area under a curve is hard. We don't learn how to do it until 12th grade calculus. Finding the area of a rectangle is easy. We probably learned it in elementary school at some point. I love when that happens. Go away. All right, go away, random weird class list. Go away, Excel. There we go. All right. So anyway, we have a 2 by 6 rectangle here. So we've got 2 times 6. Looks like we have a 2 by 8 rectangle here. I'm going to rewrite that to 8 times 2. I'm also going to rewrite this to 6 times 2. just generally the way I usually put the width second, so just to stay consistent. And then I've got another 6x2 rectangle, which gives me 12, 12, and 16. So the area under my 3 rectangles is 24 plus 16, 40. All right. All right, let's do the same thing, but this time with a right Riemann sum. So the difference here is rather than picking my height looking at the left end of the interval, I'm going to pick my height by the right end of the interval. So now between 2 and 4, I'm going to go up to this height and come over to the left. This height and come over to the left. What's the height for my third rectangle? Yeah, it's 0. I mean, we know when we don't use a lot of intervals, we don't get good estimates. So yeah, so that one's actually 0. So I've got 8 times 2 plus 6 times 2. And then plus 0 times 2, just to show that we have 3 rectangles there. And now I just have 16 plus 12, so 28. Alrighty. So we have left, we have right, we also have midpoint. So let's split the difference there. Let's not just stick to the left, let's just not stick to the right, let's go in the middle. This is why I used widths of 2. So now between 2 and 4, I'm going to use the value at 3. So don't think of that as 2 separate rectangles there. I was just showing you where I was getting my height from. And then you can see, especially in this example, I've completely, split sort of the issue of, I don't want to say completely, but it definitely splits a little bit of an overestimate with a little bit of underestimate, all in the same rectangle there. I think, if I'm not mistaken, do I end up with that exact same height twice? So I need the height at 5, yeah. So if you take a look back at what our function is, they do look pretty close to the middle, right? Our function is 1/2 x squared, 4x minus 1/2 x squared. So that's kind of telling us, if you plug a whole number in there, your fraction is going to have a denominator of 2, right? Because this is going to be a whole number minus something over 2. So those are, in fact, right in the middle. So we have these are exact values. We aren't estimating based on having the function, but we have 7.5 times 2 plus 7.5 times 2. And then this one is 3.5 times 2. So altogether 1530, and then this is another 7, so we ended up with 37 with this approximation. Okay, so in the first 3 types of sums, based on where we decided our height of our rectangle was going to be, we drew a rectangle with the intervals that we were looking at. Our last type of sum, and I think what you'll see here is that I think we're going to do the best job of estimating on this one. Rather than drawing rectangles, we're going to draw a trapezoid. What we're going to do here is we're going to use both the left and the right, and not draw a rectangle with a flat bottom, but actually connect those 2 values to form a trapezoid. Okay. So remember what a trapezoid is. A trapezoid is when only one pair of the sides are parallel, right? You've got a pair of parallel sides and the other one aren't. Normally, especially in geometry, we usually draw them the other way around, not always. So they are kind of standing up on their side rather than the normal orientation we usually expect them to be. Does anybody remember what the formula for the area of a trapezoid is? Right. You average up those two bases and you multiply it by the height. So a trapezoid is, you need to think of it as a 1/2 in the front. I usually write B1 plus B2 over 2. That does the same thing, times height. The thing about that formula compared to what we have, the bases in the trapezoid formula are sort of the things we're thinking of as heights in this, right? So kind of weird with our words, just the way it's worked out. So these are our two bases. Our height is actually our width. So anyway, to do this one, what we're going to do is we're going to average out those two values. So it's going to be 6 plus 8 over 2. And then times our height of our trapezoid, which is the width as we think of it on the graph. Which in this case is really nice because we're dividing something by 2 and then multiplying it by 2. They'll just cancel out, yeah, when we do our math. So we're going to have that. We're going to have that, I believe, a second time, just the way that this one's designed. And then in our final example here, we don't actually have a trapezoid. We have a triangle. So I've got 6 plus 8 over 2 times 2 plus 6 plus 8 over 2 times 2 again. Plus, and in this case, it's going to be, if I'm following the formula, it's 6 plus 0 over 2 times 2. But if you use the area formula for a triangle, you just wouldn't have the 0 there, right? You'd do base times height divided by 2. And we just have 6 times 2 divided by 2. So it looks like we have 14 cancels to give us 14, another 14, and then 6. So we've got 34? Yeah. That's clearly an underestimate or an overestimate? Underestimate. Do you see how it doesn't really leave a lot of space not accounted for, though? Yeah, that's why, of the approximations, the trapezoidal, especially if you really, really bring the intervals in close, is going to give you your best result. Okay. All right. So let's talk a little bit more about the overestimate versus underestimate thing. This is sort of 50-50 here. They want you to remember some things, but then some of it you can just draw a little sketch to figure it out. The one thing that you have to remember is that if we're talking about either left or right Riemann sums, whether the function is increasing or decreasing will tell you whether you're an underestimate or an overestimate. Okay? So this is the thing to remember. If you want to know if you're an underestimate or an overestimate and you're talking left-right, it's all about increasing or decreasing. You can draw yourself a quick sketch to figure it out. Draw an increasing line. Draw a quick left Riemann sum. Does a left Riemann sum under or overestimate an increasing function? Right, under. But then if I did a right Riemann sum, it would clearly be an over. And these are going to be completely reversed. This is why you don't want to remember all of this if your function is decreasing instead. Now when I go to do the left Riemann sum, I'm clearly an overestimate. And the right Riemann sum would be the underestimate this time. I think that's the announcement spell. Is there normally an announcement spell?
The schedule says the bell rings at directly on.
Okay, I don't know where I got the 10:05 from.
That's when the next period starts.
Okay, sorry about that. Okay, anyway, that's a good spot to stop anyway. This should have the word under here. We'll see you guys tomorrow. If you did not get E1 done, get E1 done tomorrow night. I plan on looking physically at your E1 tomorrow when you walk in. I will post the video to Google Classroom if I don't email it to you individually. I have it as my notes there if you need any more of it. What you need to do, E1, is the end of the video. The stuff that looks like Mr. Bean stuff is what you need. Oh yeah, look at that, 10:05 to 10:05. I just totally messed it up. You're not, correct. We may not all be. We probably all won't be here. But you'll be here tomorrow, and I will give you two things: what we'll do if we're physically here and what we won't.
Packets, so like Monday.
Perfect. Yeah. Yes. No, I'm going to tutor. My plan is if I test negative tomorrow, I'm going to tutor. I'm going to check and see if I said this right before you walked in. I'm going to check to see if Kalanick is going to tutor tomorrow. She was supposed to tutor Tuesday. It's just an option. If you don't want that option, I understand. And if you, yeah, if you do want that option, I also understand. Yeah, you know what? I'm going to Wix's room anyway, so I will probably grab you. I'm sorry about that. If I knew where it was immediately and we didn't have a half period, if either of those things weren't true, I would have dug it out for you. But let me print it out. Yeah, go up for it. I might even just have you. You had Wade 2 periods in a row, right?
Yeah.
I just might have you do it in there rather than coming over to my enhancement class, which is a pack of raving lunatics. Sorry about that, Adam. But yeah, I'll print it right out now.